Encourage y'all to be there. Any questions before we get rolling? Okay, so we looked actually at some examples last time. Did a bunch of things with the class group, and then I showed you what quadratic rings of integers look like. You get the following theorem. This is building up to one of my very favorite theorems, actually. I've mentioned this at least in passing, so here, let R. Let me be precise about what I mean. Ring of algebraic integers is the integral closure of Z in a finite extension so this is a finite extension. Now, I do write this Q alpha, and you might think that I'm specializing, but there's actually a theorem that says that, in fact, there's a primitive element there, so I can do this, but you can take this to the finite extension. You can write a finite extension in that form. R is the integral closure of Z in this field extension. So basically what R is it's every element of that bigger field, Q adjoined with alpha, that is a root of a monic polynomial with coefficients in the integers. We know that this is a Dedekind coefficient. For two reasons. Number one, this one's Dedekind and the extension's finite. Those were the two things we needed by an theorem. But in the ring of algebraic integers case, it's ultra sexy because it's got a couple of nice properties. Then all of them has following. Number one, the class group of R is finite. Right? So there are only finitely many ideal classes in the class group. And number two, any ideal class in R or in the class contains many primaries. So that is so for example, these are all prime ideals. I sort of picked these ideals to be prime in this class. But actually, each one of these classes contains infinite other prime ideals. And in fact, all these ideal classes contain ideals that are not prime. Let me give you an example. This ideal is prime. You can check this fairly easy. Call it P
P squared is in this class. Right? And it's certainly a non-prime ideal because it's square root of prime. So if you square this one, it's in this class, right? Or if you square this one, it's in this class. So every ideal class contains, in fact, every ideal class contains a prime ideal, and to make it non-prime, just multiply it by a principal ideal that's not trivial. Right? Just for fun, this one, of course, is one ideal, but it's not prime because it's not proper. Anybody think of a prime ideal in that class? That is the prime ideal principle, and then proven. I bet I can. Class one is equals to class two. Yeah. 23. That's one. Anybody know how? I haven't given you enough really to get, but I've given you enough information to make it a suspect. You write 23 as square root of 14 squared. Sure. For example, a 3 equals 1. Notice that the norm of 3 plus square root of 14 that problem is so this is not prime, of course, but that one is. Right? So this ideal right here is prime. There's another way as well. Anybody think of can anybody give an example of an integer, an ordinary integer that actually is prime here? I think 11 works. I think 11 is the smallest. Um, um, I'm trusting you here, but I think it's working. Anybody improvements? Well, I think this might be, we'll see if you can, see why you think that, all of this should be true. Let me give you a definition. Through 11, an atomic domain oh, somebody remind me what it means to be atomic? Every non-zero nine needed to be factored into irreducible, so you can break stuff down. Right? Is said to be a domain, and the atomic domain is said to be a half-factorial domain or an HFD if so what I mean by irreducible factorizations is all the alphas and all the betas are irreducible, then necessarily in so of course, the first thing here to make a definition is you don't want to be a complete tool to make a vacuous definition, right? So, okay, do these things ever exist at all? And I can think of a large class of domains. This parts. Anybody get an example of a half-factorial domain? Okay, right. I was waiting for somebody to say field, right? Because a field has no non-units, non-zero non-units at all, right? But yes, you have these satisfy this, right? Of course, now the real question is this equivalent to UFD? So in other words, if I say that all factorizations are of equal length, does that mean that it's UFD? Well, that's a little tricky, right? I mean, I wouldn't have bothered to write 5 lines on the board if this had been vacuous, probably, but that's not proof, right? Especially since it's me we're talking about. So the first thing that we should probably do is convince ourselves that such an answer exists. So, and I'll give you a genesis of the terminology too. So, let me give you an example. By the way, the terminology half-factorial domain appeared in literature the first time in 1976, I think, and then in a follow-up paper, both by the same author, a guy named Abraham Sachs. And the first paper, I think in 76 was in the, if I've got this right, I need to check my facts and go back, but I think the first paper in 76 appeared in Bolton, the American Mathematics. Bolton, yeah, it was. I think it appeared in Bolton, the AMS. It was on the half-factorial domains, and the next one was in 1980, longer paper in the Israel Journal, good journal, on half-factorial domains. When Sachs first talked about this, he did not make the assumption that it was time. He just assumed any two factorizations they claim at the same plane, right? And you don't have to make this assumption, but it's wilder and weird. You don't have the top assumption.
And so whenever you hear half-factorial domain now, since say 1990, it means atomic, even though originally Sachs actually didn't use this in the original definition, but in the paper itself, he quickly moved to a case where it was atomic. So a lot of his theorems run this.
You have an example of something that's not atomic?
Oh, yeah, sure. Uh, I'll give you, any valuation domain that's not Ethereum, will be not atomic, right? In fact, valuations are atomic if they don't get from Ethereum. For general rings, atomic and Ethereum are very far apart. To say something that's an Ethereum is much, much stronger than to say something, atomic can be really kind of really wonky rings, but for valuation domains, they're the same. So for example, yeah, so for evaluation to be atomic, it's got to be one dimensional, because all Ethereum ones are dimensional, and you also have to have caveat. One dimensional non-discrete valuation domains, essentially speaking very loosely, you can keep taking roots of them, so there's no irreducible, there's only some root in it. Under some constructions, that's a little fast and loose. And with higher dimensional, in a valuation domain that has more than in a valuation domain, well, to be atomic, you better have some atoms, right? If you're not a field, you were going to evaluate such field. It turns out that if a valuation domain ever has an atom, it has to be in the maximal ideal and not in any other smaller prime. So if you have maximal ideal here and you have something y here, then y can never be written as a product of atoms, because in a valuation domain, there can be at most one atom, y. What's the basic definition of valuation domain? Any pair of elements, one of them divides the other. So suppose you got two atoms, call them Bill and Fred. All of a sudden, Bill divides Fred, and Fred divides Bill, and they're associates, right? I think those two guys are always hanging around. So there can be at most one atom, right? And so take something in a smaller prime ideal, y, that's not it's actually in a smaller prime ideal. For this to be a product of atoms, it has to be a power of x. So that means that y is a power of x, but this is a prime ideal down here, which means one of the powers of x has to be down here, which is positive. Right? Let me give you something that's in the spirit, and you can wrap your head around it better. This one's kind of a funny example, because if I replace that z with q, that's actually, in fact, it's Euclidean domain, right? But if I pull back, if I look at the subring, it consists of all polynomials with rational coefficients, but I demand the constant term is an integer. This isn't even atomic. And the reason is you can't factor x into atoms. In fact, let's try to do it. If you can factor x into atoms, atom 1, atom 2, atom k, times b, then
precisely one of those atoms has to have degree 1. Agree? Exactly one, because it's a degree argument here. Degree 1, one and only one of these has degree 1, right? And we'll call it B. So this is the form A1, A2, AK, and let's see, B is X times Q. Right? Where these atoms now are integers, right? Because they're constant terms. And this in Q is a rational number, right? But by assumption, you're assuming these are all atoms. Now the integers are no problem, but this one is a problem because QX is the same thing as 8675309 times Q over 8675309 X. And that's my shout out to Jenny. So you can't factor it into atoms. And I'll give you one more because I want to make you be really careful before you ever ask me another question again. So here's another way that you can build something that's not atomic. Now we've seen that we can build rings of algebraic integers by taking a finite extension, right? Let's go the other direction. Let's go all the way up to the algebraic closure of Q. Right? The integral closure of Z in this is called the ring of all algebraic integers. This is not a field. For example, this Z bar has all kinds of stuff in it. It's got like the square root of 2 and the square root of 2 plus the square root of 3 plus the square root of 5 over, well, 1, say. But it doesn't have 1/2. It doesn't have 1/2 and have 1/3 and things like that. And that's actually fairly easy to prove. We know from class, this is a proof of domain. That's an algebraic extension. So this guy's a proof of domain. In fact, it's a basic domain, but it's not atomic. And the reason it's not atomic, let me kind of explain this to you. I can give you something more hardcore if this isn't satisfying. Is suppose you have an atom, call it A in Z bar. Let me point out that the square root of A is also in Z bar. So, oops, there's your contradiction because you can always split an atom A, what you thought was an atom A, into the square root of A times the square root of A. And of course, if A is not a unit, then the square root is not a unit. So we factored it not true. So there's kind of a family of things that are not atomic. This one's even worse, right? Valuation domains. If the maximal ideal is principal, valuation domains always have an atom, but if they're not in a theory, they're not atomic. This one has plenty of atoms. And in fact, it's what we call an AP domain because it turns out that all the atoms of here are in fact prime. This one here, this has no atoms whatsoever. And is unfortunately called an antimatter domain, actually. So, right, but what we call this here is a half-factorial domain, right? And the half-factorial domains are the ones that are atomic, and any two factors that just have the same length. So, of course, as we pointed out, any UFT is but this is extremely unsatisfying because I'd really like to know that what we've come up with is a new class. I'm going to show you a large class through this very famous theorem of HFD, but first I'm going to introduce you to a family of HFDs that are easier to wrap your head around. So consider these two constructions. This is very similar to that example that I just gave from the K, the Z plus XQX. These are called D plus N constructions. Notice that these are subrings of very nice rings. This is a subring of Fx, which is Euclidean. And this is a subring of F power X, which is Euclidean as well. These domains are always and they are UFDs if and only if, but I want to guess, what condition do I have to have on fields K and F to be UFD? You have to have equality. The only way with these things, with these constructions, so for example, if you have Q plus XRX, or if you have the reals plus X complex X, these are HFDs that are not UFDs. I'm gonna actually, let's look at the power series case, because actually, there's something about power series here that makes the, I think I'll probably throw a homework problem at you to verify the polynomial. The polynomials, it's not much harder, but you have to do a different technique, as you will see momentarily. Okay, so yeah, and I'll follow up with this as well. Let me prove that these are HFDs. So consider. So these are the formal power series that look like this: K0 plus alpha 1x plus alpha 1x squared. K0 K and the alpha i's. Now, I think a good approach to this is the first thing that we have to do is figure out what my unit or what my irreducibles look like. So the first thing I want to do is I want to classify. So I'll make the following. Yes. I'm sorry, not the units. Actually, maybe thinking what the units look like also might help. For sure, you need to have one condition on K naught. Anybody know what the condition on K naught is? Agreed. It has to be zero. What happens if K naught is not? Then it's a unit. I agree. Because as an element of the bigger ring, F power X, it's a unit, but the inverse of K naught is still in the field K, and you don't care about the rest of the terms, so I can still dig a unit. Okay, so now I know that the irreducible must look like that. There's one more condition. Anybody see what it is?
Some alpha I.
Something. Well, I'll give you a hint. It's actually the only condition you need is something alpha one. That's exactly right. Let me verify this. Suppose. Yeah. Not zero. And this is a unit. So, A zero is zero, so we got that, right? And let me call this pi. So I don't have to write power series. So now power is alpha one x, that's alpha two squared. Now, if alpha one is equal to zero, then now notice if alpha one, so we've established K zero must be zero. Now, if alpha one is also zero, and my power series starts with the x squared term, well, of course I can pull an x out of this, and this is of course still an element of R, because again, my power starts at x, I don't care. And here we have non-unit, and that's a problem. So this establishes this direction. Now for the other direction. So now it suffices to show that if K zero is equal to zero and alpha one not zero, then anybody know how to do that?
Or the fact that put the coefficients of these three. One of them.
Okay, that's right. That's right. That's one way to do it. Actually, another way you can do it is you can think of this as an element of F power x. And notice that in F power x, this is x times a unit, right? Which means it's irreducible and bigger range. So, but actually, I like what you've done. So if pi is, suppose we can factor it as F times G, this is, so what Grant said is just focus on the least degree term. If you factor pi into smaller things, then one of them has to have least degree term one, right, which is no problem, but that forces the other one to have least degree term zero, which must be a unit. Okay, so now I know what the units, or I'm sorry, now I know what the units is. So let me kind of recap this for a moment. Is a unit. K zero is not zero, and irreducible. If K zero equals zero and alpha one constant. So any irreducible is like this. So let me make this observation. Well, recall this thing, let's think of this as a subordinate power series. Pi is alpha one x, it's alpha two x squared. It's irreducible. If and only if pi is x times u of x, with u of x in x. This will be convenient because what this means is any irreducible down here can be thought of as an irreducible from the power series. Well, it can be thought of as x times a unit from upstairs, right? Because notice, once I've got that x there, I can multiply it willy-nilly by anything in that power x, because I'm allowed to have coefficients of x from the power x up, right? I've made enough observations now, I think, to sort of get an HFD out of this one. So we now show first we need its atomic. Well, suppose F R and R is non-zero and non-unit, then F is equal to alpha k x k plus alpha k plus 1 x k plus 1 plus whatever, with k greater than or equal to 1. But notice that this is x to the k minus 1 times alpha k x plus alpha k plus 1 x squared. And of course, I'm assuming I didn't write it, but I'm assuming that alpha k is not zero. This is the first non-zero. Notice that if that this is either a product of irreducibles, right? Each x is irreducible by our earlier arguments.
Or in the extreme case of K is one, this is unit, but in any case, this is irreducible as well. So now we have shown that F is actually a product of irreducibles. This is either a unit or K minus one irreducibles, and this is an irreducible. So, R is common. And now, all we have to do is count the factors. Then F is equal to alpha K, X K, plus alpha K plus one, X K plus one. With K greater than or equal to one and alpha K zero. Notice I'm going to use this fact again. Every irreducible X times U of X by root every irreducible. So if F can be written as alpha one choice, let's say G1, G2, GL, with GI, and irreducible in R, then each GI is X, UI X, unit, which means that L should be the least degree of F. So actually, we get a little bonus out of this. Every factorization is the same length, right? And every factorization is the same length, and that least degree tells you how many factors are in each factorization. Right? So the L irreducibles I factored in, that leaves depends only on what that K is, right? So any factorization is. Everybody okay with that? And I guess maybe the last thing I should justify is notice that if K equals F, is complete. Hence, unit. But why is this condition necessary? See if I can see why it's necessary. Let me give it. Suppose. Now suppose there exists, let's see, lambda. F not K. So let's suppose that F is genuinely bigger than K. My claim is this thing, we know it's an HFD. My claim is it can't be a UFD anymore. Does anybody see a bad factorization?
It's gonna make me feel icky. Ooh, I know how to back this. I see another way to back using this. Now, if this is a unique factorization domain, what has to happen is there's a rearrangement of this, and of course, these two factors are the same, such that this pairs off without loss of general output. This one and this pairs off here. Where x and lambda x vary by a unit in the ring R. The lambda ain't there. Right? And that's the problem. In fact, for example, if you look at this ring right here, if you look at x squared, every single factorization of x squared has two irreducible factors. But there's uncountably many factorizations as you run through all the different things here. Don't vary by unit, right? Pi x, 1 over pi x, you can just go crazy. Radical 2x, 1 over radical 2x, and so forth. Okay, any questions? Okay, so I have just enough. I don't know, I think this next theorem. This actually predates HFDs as far as terminology goes. There's a famous Jared, was it you that I had looking at the Narcadish book, that big thick biblical looking thing? So many years ago, there was a challenge issued by Narcadish, a very well-known Polish number theorist. And the challenge was something like this. Everybody knows that if you have a ring of integers, class number 1, it can only hit UFD, right? I think it was kind of open-ended. He said, he may have actually specifically said in the challenge, what does class number 2 mean? But the question was, give sort of an arithmetic characterization of what it means for higher class numbers, in particular class number 2. There was a paper written there. And this was the content of the theorem in answer to, at least in partial answer, to Narcadish challenge. Let R be a ring of algebraic integers. Then R is an HFD. Of course, this paper didn't use the terminology HFD because the paper actually predated that terminology. But it's the content. R is an HFD. It can only your class to less than or equals. This is a beautiful, beautiful theorem. Of course, this also does something else. It breaks up what happens into 2 easy pieces. Class number 1 means UFD. Class number 2 means an HFD that's honestly not a UFD. And I have brought this paper up to several deans before we have to make arguments in mathematics. This paper was published in 1960, appeared in the Proceedings of the AMS. It is a work of art. It is like a page and a half, maybe, and that's it. And it got virtually no notice at all, maybe a couple of citations for the first 30 years of its existence. And it has been cited a zillion times. But the major citations for this paper did not start until 1990, 30 years after the publication.
So is this Carlos?
Yes, Leonard Carlos wrote this paper. Yeah, that's right. Okay, any questions? I encourage y'all to hit up the math club if you got a chance. Other than that, have a good weekend and we will see you on Monday.